What is the determinant of the identity matrix? I want to compute a specific determinant. Well, here's a 4 by 4 identity matrix, and I want to compute its determinant. And we know what the answer is supposed to be. The determinant measures the scaling factor between the output volume and the input volume. But this is the identity matrix that just takes its input to its output unchanged. So the scaling factor between the output volume and the input volume should be 1. All right? The determinant of the identity matrix is 1. This is morally why the determinant of an identity matrix is 1. But I want to relate that fact to our other more computational understandings of the determinant. Now, the Leibniz formula tells us how to compute the determinant of an n by n matrix M. It's going to be a sum over permutations of n items. And what are we summing? Well, the sign of the permutation times the product of certain entries in this matrix, the sigma ith entry of the matrix M. Let's compute. So the case that we're interested in is this one, where M is an n by n identity matrix. So what's the M sigma ith entry in this case? Right, so I want to compute what M sigma I is equal to. Well, let's think about what the identity matrix looks like, right? The identity matrix is zeros except down the diagonal where I've got these ones. So an entry of one of these identity matrices is 0 unless the row index equals the column index, and then it's a 1. And what that tells me is that M sigma I, when M is an n by n identity matrix, well, this quantity is 1 if sigma I is equal to I, and it's 0 otherwise. It's 0 if sigma I isn't equal to I. What does that mean about the product of all the M sigma i's? Well, this is great. I'm trying to figure out what M sigma I is. When I multiply them all together, I goes from 1 to n. And I know what M sigma I is equal to. It's equal to a 1 if sigma I is equal to I, and it's a 0 if not. Well, then some of these terms might be 0, right? If any of these terms is 0, then this product is 0. And that means the only way that this product can be non-zero is if every single one of the M sigma i's is equal to 1. That means that all of the sigma i's have to be equal to I. And what does that mean about sigma? Well, that means sigma must be the identity permutation, right? So another way to say that is that this product of M sigma i's is equal to a 1 if sigma is the identity, if sigma I is equal to I for all I. And it's equal to a 0 if not, because in that case, some sigma I isn't I, and that means some term in that product is 0, which wipes out the entire product. So either every single term in that product is a 1, and that's when sigma is the identity permutation, or there's some term in that product which is a 0, in which case that whole product becomes 0. So all the terms vanish except for the term corresponding to the identity permutation. So every single term in this sum vanishes except when sigma is equal to the identity permutation. And in that case, what's the sign of the identity permutation? Well, it's 1. And that means the determinant of an identity matrix is equal to 1. That's a pretty painful argument. I mean, it involved a lot of reasoning about permutations. So there's some other ways that we could get at the fact that the determinant of an identity matrix is 1. Well, like the determinant of a 2 by 2 identity matrix is 1 times 1 minus 0 times 0. The determinant of this 2 by 2 identity matrix is 1. And maybe somewhat humorously, the determinant of the 1 by 1 identity matrix, which is just a 1 written as a matrix, the determinant of that 1 by 1 matrix is, not too surprisingly, also 1. Now we could use cofactor expansion to build our way up into more complicated examples. Let's actually jump right into the 4 by 4 case. So I'm going to compute the determinant of this 4 by 4 matrix, and I'm going to do it by doing cofactor expansion down the first column. So what does cofactor expansion tell me? Well, tell me the determinant of this 4 by 4 identity matrix, which I'm just writing the ones down the diagonal there, is, well, it's this first entry, this 1, times the determinant of what's left over when I cross out the first column and the first row. So it's 1 times the determinant of what's left over, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. And then I cross off the second row and still the first column, and I'm going to subtract 0 times, well, the determinant of what's left over, and I'm going to add 0, because that's a 0 there, times the determinant of what's left over, and I'm going to subtract 0, that's this entry here, times the determinant of what's left over. Now, something quite nice happens. I've done cofactor expansion down a column, most of the entries of which are 0. And what that means is that in the cofactor expansion of this determinant of this 4x4 matrix, I'm multiplying these cofactors by these entries which are 0, and that means that I don't even need to concern myself as to exactly what those cofactors end up being. Only one term survives. It's the first entry in this cofactor expansion. It's this term right here. And I got that term by taking this 1 and multiplying it by this minor, the determinant of this matrix here. And that's just a smaller identity matrix. So what we've shown is that this, the determinant of the 4x4 identity matrix, turns out to be equal to the determinant of this matrix, right? It's this matrix right here. And what is the determinant of this matrix? Well, that's the determinant of the 3x3 identity matrix. It's 1, 0, 0, 0, 1, 0, 0, 0, 1. So in general, doing cofactor expansion down, say, the first column of an n by n matrix gives you the following. The determinant of an n by n identity matrix, which would have n ones down its diagonal and zeros off the diagonal, well, that determinant is equal to the determinant of an n minus 1 by n minus 1 identity matrix, which then would have n minus 1 ones down its diagonal and zeros off its diagonal. Now we can make use of that general fact. If I want to compute the determinant of the 3x3 identity matrix, well, by that general fact, after doing cofactor expansion, say down its first column, the determinant of this 3x3 identity matrix is the same as the determinant of the 2x2 identity matrix, which we already know to be equal to 1. And we can also handle the 4x4 case. This determinant is the determinant of a 4x4 identity matrix, which by the result is the same as the determinant of this 3x3 identity matrix, which by the result is the same as the determinant of this 2x2 identity matrix, which is equal to 1. And consequently then, the determinant of the 4x4 identity matrix is also equal to 1. Well, this sort of argument comes up a lot in linear algebra. There's just a ton of opportunities in linear algebra to think about mathematical induction. And I hope you're excited about mathematical induction. And I hope you're not too excited about This is called mathematical induction. There's a lot of opportunities in linear algebra to think about mathematical induction. It's a very powerful technique. And I hope you're really excited about mathematical induction. And I hope you're not excited at all about computing the determinant of the identity matrix in any one particular way. I mean, what you should know is that the determinant of the identity matrix is 1, but then you should have some fluency to be able to think about that fact from a variety of perspectives. And that might mean thinking about that fact geometrically. It might mean thinking about it via the Leibniz formula. It might mean thinking about it via cofactor expansion and mathematical induction. But the point here is not just to have one argument or one reason why something is true, but to be able to make a lot of connections between these different concepts and different ideas to really have a deep understanding of what the determinant means.